Fredericton here, and I'll be your host for today. Firstly, I'd like to make two announcements. The first one is, you might have heard of the earthquake in Nepal recently. There's been a lot of effort to try and rebuild the community, but somebody deeply meaningful to the astronomy community has been affected. The university, Triple University, has a very active astronomy department, and their lab has been destroyed in the earthquake. So the grad students are trying to help raise money to get them new laptops and a power source and other things they need. There's currently 20 grad students who can't continue with their work. So we really appreciate if you can spare any donations for them. We've got 3 boxes, one at the front and 2 as you exit.
Unless you go super quick, because we have to get there first. Right?
Anyway, the second announcement is that there is an Astro on Tap happening on the 21st of May, Thursday. What is Astro on Tap? It's beer and astronomy together. So there'll be lots of exciting mind-expanding games, competitions, prizes, chances to talk with UofT astronomers one-on-one, all put together with a pint of beer. The event is for 19 plus. It's being held, there it is, at the Transact Club, and it starts at 6:30. There is no entry door fee, so just go as if you're going to the bar that day, but there'll be astronomy prizes and competitions. All right, those are the announcements. Let me introduce to you today's speaker, Lauren Hetherington. Lauren is a grad student here at the University of Toronto. She is going to be talking about light echoes today. Cosmic déjà vu. What is that? I will let Lauren explain.
Hello, thanks for the introduction. So yeah, my name is Lauren Hetherington, and I'm going to talk to you about cosmic déjà vu, or echoes from a supernova. So this image right here that you're looking at right now is an image of V838 Monocerotis. So before 2002, V838 Monocerotis looked not particularly remarkable. It was just a star right around there. Nobody particularly took note of it. But then early in 2002, it did something very exciting. It all of a sudden became very, very bright, about 1 million times as bright as our sun, and just increased to many factors of its original brightness. And then, as astronomers were watching it, just the way it faded away, and it had a few more outbursts that were visible in the infrared. It was, it doesn't particularly match anything else that we've seen before, and exactly what it is kind of an open question. The detail about it that I want to talk to you about is the stuff that's all around it. So this is an image of the star and its surroundings in May of 2002. So the star is that red thing in the middle, and then it's surrounded by some gas and dust which is being illuminated. So the exciting detail is you just step forward a few more months and it looks like that. A few months more, it's kind of like that. And then by December of that same year that it had an outburst, so in December of 2002, it looked more like this. And then 2 years later, pay attention to, I think, these 2 stars, because the scale's going to change. It looks more like this, and it's more than double what it was originally. Here they all are on a single composite image, just to make it clear. Every one of these images is on the same scale. So what we seem to be seeing happening here is the star has some very bright outburst, and then stuff around it looks like it's expanding at a very, very high rate. But we know approximately how far away it is, and we can see how big it is on the sky, so we can figure out how fast it's expanding. And if we work it out, in a span of 7 months, so from May to December, the apparent size of its surroundings expands from 3 light years to 7 light years, which would imply, if we take it at face value, that the surroundings are expanding much faster than the speed of light, which isn't really a thing that happens. The speed of light, it's kind of a speed limit in the universe. So right off the bat, we can say that something else is going on here. It's not dust that's been thrown off and is flying away at faster than light speeds. Something else is happening. So here's a little diagram with a star over here, and there's Earth over there. And we're sitting on Earth, we're astronomers, and we're looking at it. So when we're watching it on the sky, and the star suddenly becomes a whole lot brighter, the light that we're seeing when it becomes much brighter is the light that has followed a straight line path from the star to us. So that's the light that we're seeing when we're looking at a star, looking at V838 flash, basically. So stars, they aren't giant spotlights throughout the galaxy that are all pointing at Earth. They're more like a light bulb. They shine light in every single direction all around them. So let's say there's a cloud of dust up there, just off to the side. Some of the star's light is going to go that way, towards the dust cloud. And then what happens when it hits the dust cloud is that light is going to scatter. And once again, it scatters in every single direction, but some of that is going to go towards Earth. So it's going to follow a path that looks kind of like that. So the important thing to notice about these two different possible routes that the light will travel is that this route that goes from the star to the dust to the Earth is somewhat longer than the straight line distance. That's sort of an intuitive idea. If you're going from one place to another, it's a shorter distance if you're just going in a straight line versus if you go to the side for a side trip. So what this means is that at the time that the light from the star, when it has its outburst, reaches Earth, this light that reflected off of the dust hasn't reached us yet. We haven't seen it yet. So then if we wait a few more months, maybe a few more years, after this light has long passed us, we would see, once again, we'd see the light from that outburst, but we'd see it reflected off of a dust cloud. So where have we seen something like this happening on Earth? Pardon? Maybe. I'm thinking of sound. So if you're in like a cavern or a canyon or anywhere else where the acoustics are right, and you make a loud noise, so you clap your hands or you yell or whatever you feel like, the sound, it'll travel from whatever made the noise. So first it'll go directly to your ears, so you'll hear it once. That's a straight line route. And then it'll also bounce off of a wall somewhere and then eventually come back to your ears some fraction of a second to a few seconds later. And we call those echoes. So this is the exact same thing but with light, and we call this a light echo. So we could see a light echo from basically anything that happens to basically from anything where the light from the star can reach that cloud of dust and then bounce towards Earth in that exact same amount of time. So if we have several dust clouds scattered all over the place, these different paths that the light can travel, they're all the same distance, with some variation because of the diagram quality. They all have the same, they're all the same distance, so it's going to take light the same amount of time to travel along these different paths and reach Earth at basically the exact same time. So we're going to see light echoes off of all these dust clouds reach Earth, and we're going to see those light echoes at the same time. So what the general shape that you can sort of start seeing pop out of this, you could imagine if you're trying to find every single possible route that the light could travel, so that the total length from there to there to there is always going to add up to the same thing. You get a shape that draws out sort of like this and gives us a nice ellipse. So what this means is that we can, at any given instant, we can get light echoes from anything that happens to lie on this ellipse or cross through this ellipse. So this is sort of an unrealistic drawing. It's unrealistic in that I'm really exaggerating the width of this ellipse. In reality, it would be less of it would be less of a squat football and more of a really super elongated space sausage shape. So you could potentially have this entire ellipse pass through a single cloud. So what you would see in this case is, since it passes through both that location and that location, you'd see light echoes from both of those points. And then what would you see a little bit later? Like if you wait a slightly longer amount of time, you're going to have light echoes reach you that have had to travel a slightly longer total distance. So this overall ellipse is going to expand, and you're going to see light echoes from further out. So this is kind of, just a second. Sorry. This is a two-dimensional representation. If in reality space is 3D, if we were looking at this from Earth, we wanted to figure out what this would look like, we would need to rotate the whole thing out of the screen. And what we would see is, we'd see the star, we'd see it flash, and then we'd see a ring. And then over time, we'd see that ring expand. So that matches what we were seeing with VA3 Model Sorotis, and now we can figure out that what we were watching and what we could might naively think is stuff that's been thrown out by an outburst that's traveling much faster than the speed of light. Nothing is moving faster than the speed of light in this example, or in this situation. The light that follows these different routes, these different paths, it's happily going along at the speed of light, by definition. And the only thing that's really happening here is that what we're seeing is light that has followed slightly longer, has had to travel slightly longer distances, reaching us at later times. So what we observe as a ring that's expanding at a very high rate is... Oh no. That's unfortunate. Thank you. There we are. No. Oh, that's not a good place for water to go. put it on one side.
There's a sink right there. It's half the floor. It's high.
Yeah. Sort of. Yeah. Anyway. Yeah, so what we see as something that's expanding at faster than the speed of light is it's just a it's just a result of the geometry, and it's it's just a trick of the light, you could say. So a more common picture, or a very common picture, would be that space has a lot of stuff in it. There might be multiple clouds in here between us and whatever was giving us the outburst. So we would see light echoes from both these points, or that circular region, and another region slightly closer to us. So we would see, sort of in reality, or very commonly, would be multiple rings around the star. And oftentimes, there would just be something small, or especially later on when everything is very diffuse, you'd also see incomplete rings, just little smaller arcs. And just to show you a real example of where you get something like this, and aside from VA38, you also have supernova 1987A. So supernova 1987A was well, the year we observed it is sort of in the name, and we can watch it over time, and we can watch those rings expand. And once again, we see that faster than light, that apparent faster than light motion, as the outer ring goes from about 100 light years across to 200 in 3.5 years, which would imply very high velocities. But as we now know, that's just a result of the geometry of the situation. Another interesting detail, you might notice that this ellipse of possible places where you could get light echoes also extends behind whatever gave us the outburst, the star that shone or the supernova. In addition to anywhere else and off to the side. So you're basically able to look at, you take advantage of that fact and use that dust basically as like a giant mirror that you're holding at different sides of whatever you're looking at, and you can see if it looks different from different directions. So Cassiopeia A is one example where this was done, or I think the first example where this was done. So Cassiopeia A is a remnant of a type 2 supernova. And this is an image of the cloud it left behind. The red is infrared. The green is visible light, so anything that your eyes could see. And the blue is X-ray. And it was long suspected that the supernova that left this behind might not have been perfectly symmetric. It might have had jets in some directions, or have other interesting things going on. But in the majority of cases, or basically in every case where we don't have a light echo, we only have one angle to look at it. We see a supernova happen, and then all we're getting is the light that has traveled on a straight line from that supernova to us. For Cassiopeia A, we were able to take advantage of this. We were able to find its light echoes and use those to measure the speed of the material that was coming off of it, and determine that, yeah, it was asymmetric, which is a useful observational detail because we can use that to inform our models of supernova. So another thing, so everything I've talked about so far has been either strange outbursts or exploding stars. But we also get some things that are more regular than that and repeat, and we can make the same observation again and again. RS Puppis, which is this star, is one example. So RS Puppis is a Cepheid variable. What is that? What is a Cepheid? A Cepheid is a star which varies in brightness over several weeks or up to a month or so. And it does this in a repetitive manner. So if you want to draw a plot, it gets bright, and then it gradually fades, and when it fades it becomes really dim again, and then it becomes bright again, and then that repeats again and again and again. And what's physically going on in the star as this is happening is that the whole star is pulsating. It's really bright when when it's expanded, and then it dims as it contracts, and that repeats. So you can see from this image, RS Puppis is sitting, it's embedded in this great big cloud of dust, dust and gas. So you can sort of see where this is going. We have something that's flashing or becoming really bright every month. We can detect light echoes from this. So here's a little animation that's compiled from several frames over the course of a month and then repeats. So RS Puppis, once a month it becomes really, really bright and then fades away. And then when it's really bright, it creates a light echo in the nearby dust. And it gives an effect that strongly resembles if you sort of conjure an image in your mind of a still pond, and you have something bobbing in it, something, I don't know, a buoy or something. It'll give out ripples. This gives you a similar picture, but this is light reflecting off of dust. So what do we learn from this? So what we can learn from this is we know how light echoes work. We know their overall geometry. We know that, okay, with every point where it's really bright, it's going to send out a ring. And we know that everything on that ring is where it lies along this great big ellipse of possible reflections from each echo. And then we can look at this and we can see, okay, those rings are expanding with some rate, and we can plug all this information together and we can measure a distance to RS Puppis, a very precise geometric distance. So this is important because Cepheids have a really important property where if you have two Cepheids and they have the same amount of time that they take to go through one pulsation, you have two different Cepheids that have the same rate of pulsating. We know that they have the exact same, or they have the same intrinsic brightness. So what does this do for us? What this does for us is that we can use them as standard candles. I really like this picture. So it's like if somebody has a flashlight or something, or a light bulb, and you know exactly how bright it is, or how bright it is intrinsically, how luminous it is, you might say. And if you look at it and you see that it appears to be really, really bright, then you can say, oh, that must be really, really close. Whereas if you look at that thing and it or look at this Cepheid or that flashlight, something you know how bright it is, and you see, oh, this appears to be very, very faint. It must be really, really far away. So we can use Cepheids for this purpose, because if we know how bright every Cepheid with a 1 month period, a 1 month time to repeat, we know how bright it should be. But the important detail that we need right from the beginning is we need to know how intrinsically bright those Cepheids of that period are. And that requires having an accurate distance to the Cepheids that we're using to calibrate our standard, what we're using as our standard candles. So Aris Puppis, thanks to its light echoes, we're able to measure its distance to better than 1%. I don't remember it to better than 1%. It's about 20,000 light years away. And because we're able to measure it to such precision, that improves our use of Cepheids in general from here on, which is handy. So the last example I want to talk about, bringing it back to supernova, is supernova 1572. So in 1572, people around the world saw what looked like a new star appear in the sky. And it appeared somewhere in the Cassiopeia constellation. Here's a sketch from a book out of, here's a sketch that shows its position, so that's I right there. So this new star, this supernova, was observed by many, many people. It was observed in China and by lots of astronomers throughout Europe. The most famous person to observe it, or the one who made really accurate observations and got his name attached to it, was Tycho Brahe. And this is a page out of his book, and he called it a nova stella, which means new star. So why was this important at the time? So at the time, a predominant model of the solar system and the universe at large was Ptolemy's model of the universe, which has Earth in the middle, and then everything else in the solar system is orbiting around us, starting with the moon to Mercury, Venus, the sun, and then all of the other planets. And just to make it fit with our observations, he added circles on top of circles, which just made the math work. And then outside of all this, you have this great big sphere of fixed stars. So one of the big ideas at the time was that everything outside of the orbit of the moon was kind of unchanging. So things were orbiting, but they did it with a particular pattern that was always the same. So Tycho, when he was observing the supernova in 1572, what he was able to measure, or what he was able to figure out by not being able to measure this, is he was able to see that the supernova didn't move at all day by day. It was always had the same apparent position. And what that implied was that it was very far away, much further away than the moon. So all of a sudden you have something new appearing out here in this area where nothing new is, or nothing is supposed to change. So there were a wide variety of problems with this model of the universe, and this is just one of many nails in the coffin, but that's part of the importance of this supernova in 1572. So fast forward to more recently, since there were really good measurements of where the supernova was, we know where to look, and we found it. And it's this cool thing. So this is an observation of the remnant of Tychos Supernova in the X-ray, where the 3 different colors, the red, green, and blue, are just 3 different X-ray energies. So we know this is a type of supernova, but it turns out just knowing it's a supernova isn't quite enough information to know everything about it, because there's more than one type of supernova. The first type of supernova that you might think of, if you hear the word, is what we would call a type 2 supernova, where we have a massive star, so anything more massive than about 8 solar masses. And essentially what happens is it fuses hydrogen to helium and so on and so forth until it reaches iron. It can't fuse iron, so it just keeps building up a core, and eventually that core can't support its own weight. It collapses, lots of energy is released, and the star explodes. That's a type 2 supernova. The other main type, or main class, is a type 1a supernova, which we know comes from an exploding white dwarf. So there's a few different ways you could get a white dwarf to explode, but if you grab a random astronomy textbook and look it up, the model you're most likely to see is this one, where you have a red giant and a white dwarf, and they're in orbit with one another. They're in a binary, and this white dwarf and the surface of the red giant are close enough together that the red giant is dumping mass onto the white dwarf. And the white dwarf gets more and more massive. Eventually, a nuclear runaway inside of it is triggered, and lots of energy is released, and the whole thing explodes. So in both cases, you have an exploding star. So if you're looking at these, you could tell a difference pretty easily. The way you would do it is you'd look at how the brightness varies, but you'd also look at the which elements are present in the explosion. Hydrogen versus no hydrogen, and some other details. But to do that, you would need to get the light from the supernova as it's happening. And we couldn't do that for Tychos Supernova in 1572, because at the time, nobody had a telescope with a spectrometer attached to it. We didn't have modern instruments to make the appropriate measurements. So what can we do? Are we completely out of luck? No, we can use light echoes. So we can go looking for these light echoes, and that's what people did. They knew where the remnant was, and they knew what general area to look for light echoes. So people went looking, and the way they went looking was that they would look at several different areas on the sky, and then they would look at all those areas again some amount of time later, because that amount of time later, the location of the light echo would have changed slightly. So here's one example where a light echo was found. So can anybody see the light echo in these images? Yeah, it's kind of really hazy, and it's sort of a weird thing right there. Anyway, pardon? Yeah, it's kind of hard to see if you're just looking at it. It's kind of a slightly more difficult version of a game that you might have played as kids or might still play, called Spot the Difference. So here's an example. And the basic idea of the game is you have the same image twice, but you have some subtle differences thrown in there, like some snow on Sven's nose and some frost magic, and so on and so forth. So you could go through these pictures and squint and use a fine-tooth comb, or you could cheat at it completely. And the easy way to cheat at this is if you have Photoshop or some other similar image manipulation software, you just load both of these images and subtract them from one another, and you get something like this. So, so everything that's the same between the two images will just go away. It'll disappear. There's some haziness here, and that's just because of slightly different image quality between the two images. You'd get that in astronomy too. But the things that are different all of a sudden pop out at you, like I don't know, there's some buttons on a jacket that I definitely didn't notice the first time. It becomes a lot easier. So that's what we do when we look for light echoes. So there's the two images I showed you before. I think this is the more recent one, and this one was before that. So you take the more recent image and you subtract the earlier image, and you get this image in the bottom left. And now the stars are basically the same between both images. So those go away, and you're left with this bright spot where the light echo is now, and this dark region where the light echo was a little bit earlier. So the first thing you know now is, all right, we found a light echo. That's great. The second thing is you can tell what direction it's traveling in. So if this is just a disconnected, this is just a disconnected arc or a part of a ring. We don't have a nice bullseye like we had with 1987A. So if we want to make sure that we found the right light echo, we can see which direction this is going in, and we can trace backwards from it. So we're able to do this same observation in several different locations and do the same thing from each of our observations, and then see where they all cross. And excellent, they cross in Tychos Supernova, or Tychos Nebula. And right away we know that the light echoes that we found indeed came from Tychos Supernova, which is excellent. And I mentioned Cassiopeia A earlier, so both of these are in the same general area on the sky. These do indeed overlap a little bit. And they also, in the same research, they found light echoes for both of these supernovae, and we're able to trace both of them backwards. So now that we have the light from both of these supernovae, we're able to look at how their brightness varies, and we're able to get which elements were present in those explosions. And now we know that Tychos Supernova was indeed a type 1a, and likewise Cassiopeia A was a type 2. So even though we missed them entirely the first time around, or we didn't miss them entirely, but we didn't have modern instruments, we were able to recognize what type of supernova they were from their light echoes. So to summarize, light echoes are basically just what they sound like. They're echoes, but unlike echoes we know on Earth, which come from sound, they're echoes of light, which has come from something that had some sort of burst, and then that light has reflected off of something else. And we can use these light echoes to observe supernovae or any other similar outburst that we otherwise would have missed entirely because it was historical. And even for more recent things, we can take advantage of them to sort of get multiple different camera angles of the same outburst. We're able to look at it from more than just, okay, from here to Earth, from here to there. We can look at it from multiple different directions and get more information that way. And lastly, because we know how light echoes work, we understand their geometry, we can extract information from that. We can figure out how far away everything is and how they're situated relative to each other. So yeah, thank you.
Thank you, Lauren, for that talk. Who knew? Even though there's no sound in space, we can still get echoes. Right, we have about 5 or 10 minutes for questions. Do you want to?
Yeah, sure. Hey.
So you showed an image of like a time lapse of supernova 1987A,
Yeah.
and
I'll just find it.
and you actually go to the one right after it, please.
The one right after it?
Okay, so it's etched up. It's like 100 light year when it's in July 1998, and when the light from the original explosion of the star came in February of 1987. How did that region grow to that big, or is it actually not part of the supernova remnant itself that's being seen in that ring?
Oh, so the rings that we're seeing in the light echo, they aren't necessarily part of the remnant itself. In this case, it's a cloud of dust that's between us and the supernova.
I see.
So it's not part of the remnant itself.
So that means also for when we're doing the tracing, backtracking the light, all that light echo is also a neighboring gas and dust as opposed to the remnants.
Yeah.
I see. Thank you.
Yeah.
So all the images that we get from supernova have light echoes? And did anybody, because the way you presented it, it seemed like people just thought about it recently. Hasn't this been an issue for a really long time?
Yeah, it's definitely not a new idea. I think Keptine in 1900 something.
Yes.
I think that's the first reference I heard of it, and Zwicky later on said a lot of things about it. But
Okay. So all the images we get have light echoes?
do you mean every supernova that we see? No, we don't.
Depends on the surrounding dust.
It depends on the surrounding dust, and sometimes they're just hard to find. So there are ongoing studies, like for the Crab Nebula. As far as I'm aware, are you doing stuff with that?
I'm working with someone to try and find it.
Yeah. So
Scared away.
yes. So there's definitely examples where we expect to find light echoes and we're looking, but sometimes they're hard to find and we just haven't found them yet.
So a lot of the images that we get from Hubble, do those have light echoes?
Do you mean just?
Like if we get, images of supernova from Hubble, do they have light echoes? It depends.
It depends, and they might be, but we just haven't seen them yet.
Okay.
Okay. Do you have a question?
Do light echoes dissipate over time?
As in, do they get fainter?
Or do they get fainter and a sound echo will eventually cancel itself out and dissipate?
Yeah, they definitely would get fainter over time because you're seeing light reflect off of dust that's farther and farther away from what gave you what originally caused the echo. So as you're looking at stuff that's farther away, it's going to be fainter. Yeah.
Just out of curiosity, so the gravitational lensing doesn't play any role in this neuron? The gravitational lensing.
Oh, no, not for this. Gravitational lensing doesn't really play a role for this in general. Yeah.
So when in a cloud, if like a cloud passes from the sun can actually light up the cloud, and part of the light would actually bounce within the cloud. In this case of a light echo, how much of that kind of internal bouncing would that kind of affect? Is that a factor, and would that kind of distort the light spectrum by passing through gas and maybe absorbing certain spectral lines?
So you mean if we're looking at the sun and then
Well, when a cloud goes through, we see the cloud light up on the same similar situation when light goes through on a light echo. It bounces off clouds of gas and dust in outer space.
yeah.
But when it goes through, if it goes into that, within that cloud, is there any kind of reflection off those gases, the chemicals there, and would that, say, distort any kind of light signature?
Oh.
Through, say, going through that light part of it bouncing through, would there be like a case where maybe there's a lot of hydrogen and a bit of hydrogen spectrum gets cut away, even though the star had hydrogen or some other thing imparting a false signal?
So are you basically asking if you have a cloud of gas and dust and you have some light that's reflecting off of that, would you have any absorption by the
cloud.
elements by the composition of the cloud?
Right, and then therefore distorting the light echo to the point where, kind of like if you make a certain yell, some sounds are far better than others, and you kind of hear a slightly distorted echo.
I imagine that would be the case. Yeah, I would expect probably, but I haven't read anything specifically on that, but it seems likely.
For type 1A, there's certain signatures that kind of throw things off. Or maybe I guess if you do multiple sources, then it's also very kind of iron out the way.
I'm not entirely sure. Do you want to come talk afterwards? Yeah, sure. Yeah. You're both pointing at each other.
Can I ask 2 questions about supernovas?
Sure.
For the type 2 supernova slide, can you go to that one?
Type 2 supernova slide. So the one where I just drew a model of it?
Oh, so one of the questions is, do we know the
This
rate
one?
between type 2 and type 1 supernovas?
Like the rate of how often they happen?
The frequency between the two.
Between the two?
Is one 3 times as likely, or is one 5 times as likely?
Oh. Well, we definitely do know relative rates. I seem to be blanking on the exact numbers. The relative rate of type 2 versus type 1a. Like I know the overall rate of supernova is like once per century in a galaxy, but the type 2 versus type 1a.
Oh, it's type 2s are half.
Half?
And type 1as are a quarter.
Okay.
Half, quarter. Oh, and then the other quarter would be other types.
Yeah.
Yeah.
Okay. Can you expand that slide?
Yeah, sure.
Is that so? Hydrogen, helium, carbon. Is that supposed to be nitrogen or neon?
Neon.
There's a neon burning cycle before oxygen.
I believe so, yeah.
Oh, okay. And then beryllium, boron, and lithium. There's no burning cycles for those.
Yeah, I think this is probably a simplified diagram, but
Okay. But no, then those metals do burn.
I think they're used within other reactions, so yes?
So what, neon is neon actually heavier than carbon? No, sorry, heavier than oxygen. Oxygen is carbon, nitrogen, oxygen,
Carbon, nitrogen.
fluorine, neon. If you go through.
That's a good point. We could- Yeah, sure. Yeah,
So the calibration of the Cepheid case,
yeah.
so you can get a very accurate distance and hence intrinsic luminosity, but what about the fact that the Cepheid is buried in all that dust, which presumably will dim it from our perspective?
That's true too. Well, I think in that case it might be right in front, but even if it was partially enshrouded, we can correct for any dust between us and it, because dust is going to preferentially, it's going to cause things to look slightly redder than they would, because it preferentially blocks shorter wavelengths. So if we know what spectrum we expect to see and we compare it to what we do see, we can make a correction for how much dust might be in the way.
We'll take one more question, and then I'm sure Laura won't mind staying a little while for you to ask any extra questions.
Yeah, I don't think I've asked anybody over here, so do you want to?
I don't know if you touched on this, but for the Cassiopeia stars, what exactly causes that oscillation in luminosity?
Oh. So the cause of the change in luminosity is that the overall size of the star is becoming larger and then smaller over time. And our understanding of why that happens, there's a lot of details that I'm not quite remembering, but sorry?
Oh, basically the idea is when it loosens up, when it expands, the pressure inside goes down, and that kind of causes the nuclear reactions to want to slow down and kind of maintain the equilibrium.
That's true too, but the reason why Cepheids pulsate is because one of the layers within the star itself, under certain conditions that I'm forgetting at the moment, under certain conditions it becomes more opaque, so it contains more energy within it, and then that causes it to expand. And then when it expands, at a certain point, it becomes transparent again. That light is able to escape, and then it shrinks. And then at a certain point, it becomes opaque again, and that repeats.